Okay, good morning, everybody. Okay, I hope you guys slept well and you're ready for some more calculus of parametric equations here. Okay, I'm just adjusting here a microphone so that you guys can hear me. And so I'm going to ask you guys actually be a bit patient today because I switched from coffee to green tea for a couple of reasons. Anyway, we'll see how this caffeine gets into me. I hope it does. But let's go back and let's look at our browser. And let's remember here, we're going to go to our class 262. And we have our schedule. So to remind people here, we have task 3 coming up Monday, April 4th. Monday, April 4th, we're going to have that test. So just going to remind people, make sure that you're up and running with your scanning app so that you can scan and upload. So make sure those things are in play. And I want to remind you guys, you're going to also use I guess it's an integral sheet, right? You're going to let you guys use an integral sheet, of course. And you're going to show your work. You're going to scan your test and your work. You're going to upload it the way you usually do. So I just want to, remind people about those things. So hopefully you guys are aware. And then also I'm going to say another thing. You might want to get used to set your smartphone, maybe, I don't know, a timer or something, right? Because what can happen is people think because you take this test at home, you turn it in when you're done, even if you're done 3 hours from where you start, and that's not going to happen, right? So I'm going to have the timing of the test, and then there's a small window where you actually turn it in, okay? So that's what's going on, so you guys know. So make sure you understand the details, which is, yes, you want to be timed, so you keep track of your own time. So you might want to put a, set a timer for yourself. And yes, Sam, it is May 4th. Okay, Monday, May 4th. So anyway, I'll give you guys a little more information as we proceed. So let's go to the iPad here. And I'm going to draw up from the iPad some of the notes that I created for you guys. Now, what came next really is area after the second derivative. We even now have area under a curve. I usually save that to last. Try to get that to last. So I'm actually going to go to, I'm going to go to arc length here. And you guys know where to find the notes already since we've been doing this for quite some time. You guys know where to get those. Anyway, okay, we're at arc length here. And I want to say to you again, we have our curves defined parametrically, meaning x is some function of t, y is some function of t, and t is between alpha and beta, two values, right? Well, here's an arc length kind of question where x is a, that corresponds to the time or t being alpha. X is b, corresponds to the time being beta. And of course, you have your orientation of your curve, right? We want to find s, and this is arc length again, right? So we want to find how long that is. What's the distance along the curve, even if you have parametric equations? So when I read this, it says, let C be a curve defined by parametric equations where f prime and g prime are continuous over the interval, and C is transverse. Let's see if we can get that. C is transverse exactly once over the interval, really, as t goes from alpha to beta. So it's really just over the interval is what they're saying. So if you have that, and we can determine arc length of the curve from the initial point to the terminal point. And so this is kind of the assumptions you need, f prime and g prime, meaning the derivatives of these two need to be continuous. And the reason is very simple, because when you integrate, you have to integrate over a continuous function over that interval, right? So we'll see this. And what I did here is I proved for you guys the arc length formula in parametric, with parametric equations. So S equals, this is our traditional arc length formula from rectangular coordinate system. Now remember that dy dx we seen yesterday is dy dt over dx dt. And what that does is we're going to use this formula right in here. In other words, we're going to substitute x is A, t is alpha, x is B, t is beta. And you're going to substitute now dy dx, that derivative I just wrote down, and it's right in here. And the rest is really algebra, meaning I have to take 1, which I let dx dt over dx dt squared, right? That's 1. And I add it to my y prime, really. And what you'll get from algebra is that I have the same denominator here, okay, using some algebra. And I'm going to use properties here of square roots. So I have a separate square root there. And what happens now is the definition of absolute value is applied. And, here's kind of an interesting thing. It's going to be positive there, dx dt, right? And so this is the same algebra I was using yesterday, where I'm going to actually combine that here. I'm going to use a division here with these two. And what is going to happen is I'm going to write this division as a product. I still have dx where my dx cancels. And I finally obtain here the arc length formula for parametric curves. So this is what we're going to use today. Okay, and this is t is alpha, and this is t is beta on our curve. This is the initial point and the terminal point in a sense, right? This is why we needed to know those things. Initial point, terminal point, and we're going to find dx dt squared plus dy dt squared dt. And I want to remark here that this also means that ds equals the square root of dx squared plus dy dt squared dt. So we're also going to use this as well. Okay, so I have the proof here, my proof of the arc length formula and the ds. Now you say, why do I need a ds? Because if we go further, now I proved, the arc length formula for a couple of situations where dx dt is increasing, decreasing. We can talk about that a bit later. Orientation has nothing to do with arc length. We're finding this s is what I'm saying here. Anyway, you say, why do I need that ds? Because you also can have surface area. We can find surface area by revolving about an x-axis or a y-axis. And when we do that, remember, this integral, the arc length formula, gives us this ds, is what I'm saying. And we can rotate now our curves about an x-axis or a y-axis. And again, you start with your trusty surface area is going to be the integral of 2 pi r ds. So we talk about ds because ds is applied here, right? This is what we're going to use for the ds. And this is what I have here, 2 pi r ds. Well, if you rotate about the x-axis, this is going to be a y. And similarly, when we rotate about the y-axis, right, this r becomes x, and this is still our ds here. So we got the ds. So you can actually work with both settings here when we study arc length. You could get surface area when you talk about arc length. Okay, and so now you might say, well, how do we do some examples? Well, this is what we had so far in homework. We're going to extend that, of course, today. So we're going to try to look at an example here. Remember, we're going to look at an example now of arc length and how we find that. So we're going to get the arc length here. And we know S is alpha to beta square root dx dt squared plus that dy dt squared, and we integrate with respect to this t. So remember the original assumptions that this had to be continuous. The derivative had to be continuous. They said f prime. And g prime had to be continuous over the interval from alpha to beta. So here's your example. So I'm going to look for a good example here. And start us off and say, okay, let's have x equals 1 plus 3t squared. Y equals 4 plus 2t cubed. And this is over the interval from 0 to 1 here. Okay, so, I mean, maybe we want to see a bit of this. 1 plus 3t raised to the second power. I'm gonna try to see. Let's take a look here at the browser and say 1 plus 3t squared. We're going to define this parametrically, comma 4 plus 2t cubed. And this is kind of interesting because when I look at this, ladies and gentlemen, let's look at it this way here so you guys can see. The parameters are from 0 here to t. So we're essentially looking at this particular curve here, and we're trying to find the arc length associated from, this is where t is 0 to t is 1. Now when t is 0, ironically, you start at 1, you know, t is 0, it's 1, 4, as you guys can see here, that initial point. So this orientation is going in sort of a counterclockwise direction, if I can say that. But here's the curve we're trying to find the arc length, and this is from t to, 0 to 1. So it's the exact same kind of question we're looking at. What's that length? Anyway, okay, we're going to try to find that length here. So in order to use the arc length formula again, what you need to do is you need really the derivatives, right? You need dx dt, which is d dt, 1 plus 3t squared, and we know by properties of derivatives, let's just say this becomes, we know what this is, 6t. Okay, so this is dx dt. We also need dy dt, which is the derivative of 4 plus 2t cubed. And we get 6t squared here. So dy dt is 6t squared then. Now, sometimes we just write this as x prime, y prime, because as you guys can see, this starts to get heavy in terms of notation, right? We got a lot of notation here. So we need the square root, or I should say, let's start with this. We need to square the derivative of x and square the derivative of y and add these terms. So I get 6t squared, 6t squared squared, 36t squared plus 36t to the 4th here. Okay? And, of course, we need the square roots of these. All right. So you might say, are you asking me, Mr. Judge, to, if we're going to find arc length, we integrate from 0 to 1, the square root of 36t squared plus 36t to the 4th dt? The answer is yes. But then the question people ask is, well, how do you integrate this? I don't even know of a technique that we can use to integrate. I haven't seen anything like that. Well, you're going to use some algebra. And the reason you guys use algebra is so you can actually simplify the integrand here so that you can integrate, right? So we know that. And algebra, I see what I can do here is I can factor out 36 and a t squared. I can factor out the greatest common factor. So when I do that, what I have under the radical is 36. Let me do this here. Well, I guess we can still do that. Okay. 36 t squared, and then I'm left with 1 plus t squared. Okay. So double check, like I said, I switched from coffee to green tea. And, all right. Properties of radicals, square root of 3 product rule in a sense, right? Square root of a product is product of square roots. And the square root of 36t squared is really, if you guys really want to know, it's actually the absolute value of 6t, right? Now, the interval is from 0 to 1 for t, which really means that this is going to be 6t anyway, right? So it's really, if you guys remember, this is 6t in absolute value, which comes out to 6t. So my surface area, this is t is 0 to t is 1. We get 6t square root of 1 plus t squared. And then you have a dt. So then the question now will become, what do you do? And I say, use substitution. And in this case, you'll be 1 plus t squared. And you say du dt is 2t. Or we can say du becomes du over 2t. So this arc length goes from 0 to 1, 6t, square root of u, d over 2t. You guys know the details here. T's canceled, and you end up with a nice constant of 3, and you integrate from 0 to 1, square root of u. Now this is t, and this is t, and this is du. So you guys know you probably want to change your limits. I mean, not probably. Change the limits. So you have to go back to what u is. And you say, here's my u, right over here. Plug in. This t is 0. If you plug in 0, I get 1 plus 0 squared is 1. So here, my u is 1 when t is 0. And then when I plug in the t is 1, I get 1 plus 1 squared, which is 2. So now I have u here is 2. So we'll have 3 integrate 1 to 2, u to the 1/2 du. And you'll end up with 3 u to the 3/2 over 3/2 from 1 to 2 that we have to evaluate. And this is 3 really now, we can say divided by 3/2, but you guys know it's multiplied by the reciprocal, right? So this is times 2/3 u to the 3/2, and we evaluate that from u is 1 and u is 2. So you get 2 u to the 3/2 from 1 to 2 again, which is 2 times 2 to the 3/2 minus 2 times 1 to the 3/2. So, ladies and gentlemen, use the definition here at this point of any base to a 3/2 power, right? And I can say, I know what this is. 2 square root of 2. I know what this is. This is 1. So your final answer is 2 times another 2 square root of 2 minus 2 times 1. I mean, sometimes people factor that out and they say, oh, here's 2 square root of 2 minus 1, I guess. So here's your first arc length formula in the parametric world. And there's details. The details are in the integration here. But what I showed you guys new is I proved that formula for you guys. It's also, there's another proof in your book that's more formal. You can look at that. But this is essentially how you handle, arc length. I'm going to recommend, like I said, for your test, you guys have maybe an integral sheet, right? Because I'm going to give you another example here. X equals e to the t cosine t. Y equals e to the t sine t. And then we're going to look at this from 0 to pi. Okay, so here's this integral from 0 to pi here. If you go back now, let's take a look at the browser just for fun. Meaning, let's try to enter this, see what this looks like. Okay, so I have e raised to the t power, and that was cosine of t. Okay, and then e raised to the t power, we have sine t. Oops. I think we're okay. Now we're going to see some 0 to pi. Let's see if it does that. Yeah, okay, nice. There we go. All right, so you guys can see this here. Incidentally, right, the initial point, if you say t is 0, this is the curve they're asking us. We want to find the arc length of this curve. So when t is 0, it looks like we got e to the 0, which is 1, and cosine of 0, which is 1. So we start, yes, again, at 1, all the way on the right side there. And sine of 0 will give you that 0. So it's 1, 0. So I'm not going to try to write on all this, but the point I'm making is, yes, your curve, we have an initial point and a terminal point over that interval. We talked about those. And this is the curve that they want us to find the arc length from 0 to pi. That's pretty nice. I like that. All right, let's try to get to work here. So, as you guys can see, what you really want to do, you're going to use the formula, or dx dt. Now, let's be careful here. E to the t cosine t. And here's my point. You're going to have some work to do with some of these here, okay? Meaning you're going to need to use the product rule. Product rule from calculus. Calculus 1. So this is why this is a Calculus 2 course. They assume you guys can do product rule, right? So this is e to the t dt cosine t plus cosine t e to the t. Derivative of cosine is minus sine, and then this is e to the t. So this is going to be my x prime, so I can write it. We mathematicians, we like to write it as maybe et cosine t without a minus sign, and that'll be minus et sine t. If I switch my terms, and I could even factor. And this is what we'll call x prime. So this is how we start. We need dy dt, which is d dt, and you get e to the t now of sine t. Again, we're going to use here what? Product rule. And you pull out e to the t, the derivative of sine, plus sine derivative of e. derivative of sine, again, we know is cosine. We have e to the t. So we get e to the t cosine t plus e to the t sine t. And again, I'm going to factor here. I'm going to factor out my e to the t now. So, okay, cosine t plus sine t. Okay, so this is my y prime now, right? This is the derivative. This is dy dt. So I'm going to use this, and I'm going to use this. Okay. Now, here's what's going to happen with these here. Since we need to square these, right? You get x prime squared will be, I'm gonna do them separate. I'm gonna say x prime squared. We're gonna write this down. You guys know this was, I think it was e to the t, right? So you get e to the t cosine t minus sine t. And this thing is squared, which is e to the 2t. And then I have cosine t minus sine t, and we have to square that. Yep, so just make sure I have the right term here. Now, this we're going to have to use FOIL, ladies and gentlemen. This is where your algebra comes in. So you got algebra there to do. And by the algebra, you're going to get cosine squared t minus 2 cosine t sine t. Plus sine squared t here, right? Because you say, what do you mean FOIL? Yeah, you got to FOIL that because what you have is a second power here. You got cosine t minus sine t times another cosine t minus sine t. There's that power 2 here. So that's the key here for this one. And double check, because you do the same exact thing for y squared, or y prime squared. E to the t cosine plus sine. You square this, which gives you e to the 2t now. And yeah, let's make sure we're good. I think we need another parentheses, right? Okay, so cosine t now plus sine t, you square that one as well. And don't forget, this portion is really cosine t plus sine t. You're going to use FOIL again here. And you end up with e to the 2t cosine squared t plus 2 cosine t sine t plus sine squared t. All right, so keep an eye that this is x prime squared, and then this will be y prime squared. So we're supposed to add those. Now, here's what's going to happen. I'm going to do some algebra here. I'm going to say I'm going to take this x prime squared plus a y prime squared. Now, algebraically speaking, I'm not going to rewrite everything again. It's already there. We're kind of running out of space. But what I want to say here is you're going to end up, when you add these terms, let's do it right here. Let's move it here. X prime squared plus y prime squared. When you do that algebra, you're going to end up here with e to the 2t times 2 cosine squared t plus sine squared t. I'm sorry, 2. You're going to get 2 of those. Now, the reason is very simple here. I mean, I can factor, if I said I'm going to add these, I'm going to factor out this e to the 2t. That's why it's out there. I'm left with, here's what I want to point out to you. For both of those terms, factor out that e to the 2t. Where's x prime? There it is. Here's what's left, though. You got a cosine t minus 2 cosine sine plus sine squared t. You have here a cosine t plus 2 cosine t plus 2 sine squared t. So when you factor out the e to the 2t, you got opposite signs here, right? This here is plus for the y prime, and for the x prime, it's minus. So that term goes away. That middle term goes away. You're just left with 1 cosine squared plus another cosine squared. That's why you got 2 of them. And you're left with a sine squared plus another sine squared. And again, this is why you have 2 of them out here. So yeah, there's some algebra here, ladies and gentlemen. This is what's a part of this. And you might say, can I factor now out that 2 you have? The answer is yes. So if you factor that 2 out now, you get 2 e to the 2t. You're now left with a cosine squared t plus a sine squared t. And I guess this is part of that formula sheet on our test. We can have, some of that identity there. But the point is, you end up with this nice 2 e to the 2t. Now, don't forget, that was our x prime squared plus our y prime squared. So there's the algebra, and when you take the square root of these, because this is what we need, we get the square root of 2, really, e to the t. Again, using algebra, and you say, oh, what algebra is that? Well, what's the definition, ladies and gentlemen? Isn't this e to the 2t to the 1/2 power? So we can just simply multiply 1/2 and 2 and get that t? The answer is yes. So the arc length formula now, with all that work, we went from 0, we're going 0 to pi, right? That was the original t. From 0 to pi, and that's now the square root of 2 e to the t dt. Right, so you're going to have to pull that stuff out. Now, the constant that comes out, that's square root of 2. So square root of 2 integral 0 to pi e to the t dt. So ladies and gentlemen, we get square root of 2, really e to the t, 0 to pi, square root of 2 e to the pi minus square root of 2 e to the 0. And e to the 0 here is 1. So we can say we have square root of 2 e to the pi minus square root of 2, or square root of 2 e to the pi minus 1. And here's another example of how to find that arc length. But for some of these, I'm also going to say you may need the what? You may need a integral sheet to use for some of these, and that'll be very, very helpful. Anyway, I'm gonna post some more examples for you guys online of this stuff, like I've been doing, so that will be very helpful for you guys at this point for some of these, right? Give you extra examples. But what I want to do now is try to see, well, how can we look at, for example, possibly arc length, I guess. So we're going to look at some arc length examples here for you guys. So let me take a look. Let's talk about arc length. See how that arc length works. And remember, S equals the integral, and that's a different S. Let me say this. I write this as surface area. I'm sorry, I don't want to do arc length. I want to do surface area. Apologize. So for some surface area questions, we have surface area will be the integral of 2 pi r ds. All right, so there we go. So the first example that I want to look at with surface area, let's see. X is going to equal here 3t minus t cubed. Y will be 3t squared, 0 less than or equal to t, less than or equal to 1. So here's our parametric equations. Now we're going to revolve about the x-axis. All right, so if I look at, I am on the iPad. Let's see, what do we do when we revolve about the x-axis? We're right here, right? Here's our arc length formula. Here's my point. Your radius is going to be y. So the radius is y. It's the y coordinate. So by the arc length formula here, right, we got this arc length version of ds. That's the square root of x prime squared plus y prime squared dt. We've seen this notation, but surface area now, we start by saying 2 pi y now with that ds. So let's start to fill things in now. So this is going to be from 0 to 1, 2 pi. Now, here's where your y is. Y is actually 3t squared. That's the y that they're talking about. So I have to substitute for y the 3t squared. I just need to know now what is our ds. And that's where this formula comes in here, the ds formula. So I want to say when you're rotating here about the x-axis, the radius value will be y. And the y is here. So the real work, as you guys can see so far, is finding ds. So let's try to find that, meaning dx dt, we differentiate the x coordinate, which is 3t minus t cubed. And by properties of derivatives, we know that's 3 minus 3t squared. So this is that x prime. dy dt is d dt of, what's the y value? 3t squared. And this is going to give us 6t. So this is the y prime. Square these and add, right? So you can start to do that. We can say 3 minus 3t squared plus 6t squared, which is going to give you 3 minus 3t squared times 3 minus 3t squared plus, I'm going to square this. This is 36t squared. By using some FOIL and algebra here, 9 minus, looks like it's going to be 9t squared minus another 9t squared plus 9t to the 4th plus 36t squared here. So you end up with 9 minus, let's see what happens here. 18, that's going to be plus 18 squared plus 9t to the 4th here. All right, so this is what we have, and I'm going to notice that I like writing this in descending powered terms, right? Descending order. factor out the 9. And now you have t to the 4th plus, looks like a 2t squared, plus 1. So I want to remark here, notice this. You can actually factor this because this is a perfect square trinomial. Remember, they give you questions that you can actually do, ladies and gentlemen. These aren't numerical approximation questions. They give you questions that you can, go over and, work the integral here. So this is a nice perfect square trinomial, meaning this is really t squared plus 1 squared when you factor. Perfect square trinomial. These are designed to be doable. So I get t squared plus 1 squared, and then you say, but wasn't that supposed to be all under a square root? Because this is the ds portion? The answer is yes. So I'll put this under a square root. And as you guys can see, I can replace 9 here and say, well, 3 squared is 9. This really becomes the absolute value of 3 times t squared plus 1. Okay, so just giving you this all the detail. And what, again, is going to happen is that this is from t going from 0 to pi. We know that this is actually going to be what? 3 t squared plus 1. Okay, so this is what's happening. That's going to be positive. So let's write this down. That means we have ds is a square root of x prime squared plus y prime squared dt. We just found what ds is. ds will be 3 t squared plus 1 dt. Okay? 3 t squared plus 1 dt. All right, now here we go, ladies and gentlemen. You say, what do I do with that ds? I write it here. This is 3 t squared plus 1 dt. So let's really be careful with what we have. This is the integral. All right, let's really be careful here. I think some of you guys are a little confused with the algebra. Just so you guys know some of your questions here. Notice what I did. This is minus the minus. That's minus 18t squared, and then plus 36t makes that a plus, so you guys know. Double check. Okay, so all together, let's write down the surface area formula. Surface area integral 0 to pi. So we have 2 pi times 3t squared, right? 2 pi times 3t squared. And then you say, I just found the ds. Oh, it's right above me. Good. Times what? 3 t squared plus 1 dt. This is the ds I just found. So I'm going to pull out my constants, ladies and gentlemen. I'm going to say, okay, I got 2, 3, and 3. And what does that give us? And don't forget the pi. We're going to have this equal to 18 pi over 0 to pi t squared plus 1 dt. And so what happens, ladies and gentlemen, of course, you guys know we can say, all right, I'm going to integrate 0 to pi. This is t to the 4th plus t squared, right, dt. And integrate. 1/5 t to the 5th plus 1/3 t cubed from 0 to pi, ladies and gentlemen. I apologize. It's not 0 to pi. It's 0 to 1. That's the problem. It's not 0 to pi. It's 0 to 1. So let me see if I wrote that down correct. Zero to 1. That'll make things a little bit helpful. Not 0 to pi. This is 0 to 1. So 0 to 1 here. Let's see if we wrote it down originally that way. Yeah, we got 0 to 1 here. I'm looking online, and I'm looking at actually the browser where I have pi in there. I'm looking at the wrong, you know what I'm doing? Here's what I'm doing. I'm looking at the wrong curve. Just to let you guys know. Look at this browser. That's not the curve we're doing. That's the last one. Okay, whatever. It's not 0 to pi, 0 to 1. Good. Okay, so that makes things a bit easier. So we say this is going to be (18pi) 1/5 to the 5th plus 1/3 1 cube minus the 18pi 1/5 0 to the 5th plus 1/3 0 cube. You guys know what happens here. This whole portion is 0. And this portion really, let's do it right here, is 1/5 plus 1/3, which becomes 3 plus 5 over 15, or 8 over 15. So altogether, you have your 18 pi times 8 over 15. Now, you can reduce this. 15 is 3 times 5, right? And 3 goes into 18 6 times. So, final answer. Six times 8 is 48. 48 pi over 5. And that's your surface area, ladies and gentlemen, when you revolve about the x-axis here. So let's try to consider a curve for surface area where we revolve around the y-axis. And let's get one here where we revolve around the y-axis. So let's look at an example here. We let x be e to the t minus t, and y be 4e raised to the t over 2 power. And again, t is going to be from 0 to 1 here. And maybe we want to look at that one. I don't know. Let me see. I'm kind of curious. E to the t minus t. And 4e to the, okay, so we're going to say 4 t over 2. This is 4, and that's 0 to 1. Okay, let me see if this is correct online here. Okay, e to the t minus t, 4e. Okay, 0 to 1, and let's show you guys really quick. Here's the curve they're talking about, okay? So if t is 0, I get e to the 0, I get, what do I get? T is 0, I get e to the 0 is 1. So we start at 1, it's 1, 4. So the initial point is at 1, 4. And so you can see the orientation. I won't write on that. All right, initial point is at 1, 4, and that's what we're starting way down here. Terminal point is going to be on top there. So we're trying to find that arc length. How long is that? Pretty good. All right. But this time, we revolve about the y-axis. And we're not going to find arc length. We're finding surface area. So remember, we're going to revolve about the y-axis. Go back to that curve. Revolve this about the y-axis, and we're going to find the surface area. And notice the radius now here will be, if it's surface area, radius will be actually the x value. Okay, you're going to get a horizontal radius. iPad Pro. Okay. Surface area, integral, 2 pi r ds. We say no, we know the radius is x. We just need ds. You say, well, how do you get ds? We have to differentiate. dx dt. Is d dt e to the t minus t, which is e to the t minus 1. dy dt is 4e t over 2, which is 4e t over 2 times 1/2 by chain rule, which is 2e t over 2. X prime, y prime. X prime squared plus y prime squared will become e to the t minus 1 squared plus 2 e to the t over 2 squared. Doing some algebra. E to the t minus 1, e to the t minus 1 plus 4e to the t when you actually distribute the powers here. Right? There's a power 1 if you want to do that. Go back to some I don't know, beginning algebra, right? And by FOIL, ladies and gentlemen, here, we're going to FOIL here. E to the 2t minus 2 e to the t plus 1 plus 4 e to the t. And let's double check to see if we're okay. E to the 2t plus 2 e to the t plus 1. Let's write that clear. Okay, so double check. This is our algebra. Now, if you look closely, we can factor. We have another perfect square trinomial. This is e to the t plus 1 squared. Perfect square trinomial here. So don't forget now, you say, oh, but Mr. Judge, we need this under a radical because we're needing the, find that ds. Okay. And as you guys can see yet again, this becomes the absolute value of e to the t plus 1. Now remember, this is over the interval 0 to 1, which means this is actually positive again. Probably no coincidence, ladies and gentlemen. It's no coincidence. Okay, so let's write this down. We got e to the t plus 1. This is going to be replaced here with the ds. E to the t plus 1, and don't forget you need that dt. And you say, but Mr. Judge, x was, what's our x, ladies and gentlemen? E to the t minus t. So you have to put that there. E to the t minus t. So this is how we're going to integrate and find we're going to have to find the arc length by integrating the product of this function. So yeah, radius here is x. Right there. And x is defined to be e to the t minus t. You're just plugging that in. So 2 pi e to the t minus t times the ds we just found, which is e to the t plus 1 dt. And this is from 0 to 1. Okay, here's what I want to say to you guys. You're going to need to multiply here. And when you multiply, I like pulling out my constants so I can focus on the algebra a little better. Let's see what this actually becomes by the FOIL process, right? This is e to the 2t f. O terms plus e to the t. Inner term minus t e to the t. Last term minus t. So double check here. 2 pi integral 0 to 1. Looks like we get e to the 2t plus e to the t minus t e to the t minus t dt. And yes, ladies and gentlemen, you're going to need to do, again, what? Properties of integrals. Integral of a sum and differences, the sum and differences of integrals. But I want to note here that you may say, Mr. Judge, how do I integrate t e to the t? Use what again? Integration by parts, IBP. So you're going to get to use integration by parts here to find this portion, ladies and gentlemen, IBP. So I leave that to the reader, the very famous statement that math instructors use. Leave that to the reader for you guys to finish that, right? And then we get a nice 2 pi. I'm going to tell you what the answer is. E squared minus 2e minus 6. This is the final answer that you guys get here. So, ladies and gentlemen, here's how you handle a very sort of fundamental, I should say, surface area question. We get e to the t minus t for e to the t over 2, and from 0 to 1. And then so now I'm going to give you a nice remark here about area. You might say, what about area under a curve, right? I told you I saved that to last. So what about the area under a curve? Well, I'm going to remind you guys. If I go to my notes, here's where there's something kind of interesting. I talk about area here, and I want to mention this to you guys here. There is a small thing to remember about area under a curve here, and that is what I call, or what we call, the orientation. Now, this is the only thing you have to be concerned with. If you look at this picture, when x goes from, we have here, A to B, right? The time value, x is A, corresponds to t is alpha. And when x is b, that corresponds to t is beta. So my orientation for t is going kind of left to right, but I guess I would rather say dx dt, the change in the x variable, right? X is increasing, and we say that's positive. So you're going to have an issue here with orientation. Now, I wrote it down here. I say if C is above the x-axis, the curve is transversed, move through once as t increases from alpha to beta. So you're only going through once. You're not looping. dx dt is positive. You just substitute. Okay, so you're just going to substitute here. So I'm going to kind of do something here. This is not always good, but I'm going to just let you guys know. I'm going to go to the prior example. I want you guys to know. You want to consider the prior example, right? Because that was kind of an interesting question. Remember, you can't always integrate when you make things up. So be careful here. We're trying to find the area under this curve. This is A, right? And this is what we say. A here is the y value times dx. Because remember, traditionally we say y is f of x, right? But we can't use f. F is taken for the x variable in our parametric equations. It's taken already. This is a different f right up here. So with this formula, my area is going to be here. Instead of using y, well, what was y? Let's write it down on the iPad. Let's do this. My area will be the integral y dx. So y here, we say, what's y? Well, y was defined, remember we said this is 4e to the t over 2. Now, what about dx? Well, I have to find what dx is. Since x was e to the t minus t, we know dx dt is e to the t minus 1. So that means that dx is e to the t minus 1 times dt. So ladies and gentlemen, we're just going to substitute the y variable and dx. This portion is going to be e to the t minus 1 dt. So that altogether, we have this area going to be 4 e to the t over 2, e to the t minus 1. That's dt. And then t here is going to be, here's the orientation. This is where you have to really be careful. Right? When t is 0, we know x here, if we plug in a 0, x here is 1. When t is 1, plug in a 1 now. X here will be e minus 1. Now notice something here. This is an example with the orientation where dx dt is positive, meaning x is increasing. You increased. X went from 1 when t is 0 to about 1.8. And I know I can't write on the browser, but the first point will be right here, ladies and gentlemen. Right? It's 1, 4, and then on the top. So in other words, my x variable is increasing. This is going to be a factor. This allows us to simply write or substitute like you think we should, meaning put the t being 0 down here and put the t being 1 down here, because in my notes for area, which I saved to last, we care about orientation. So I'm going to describe to you guys here, area under the curve. This is the orientation I'm talking about. dx dt is increasing, and this is just a direct substitution here. Alpha, beta corresponds to x is A and x is B. So everything's just completely substituted the way you think it should work. Now, if the orientation goes the other way, dx dt is negative, take a look at my proof. You're going to need to simply do the following. You're going to need to add a negative sign, ladies and gentlemen. And then you can still have your lower value, upper value, because t is always defined between alpha and beta. But what you'll need is a negative sign. And I actually described this here in the notes. So be careful with the orientation only when it comes to area. Only for area. But we're okay here. So, I kind of looked at this question here from the prior example, and I said, I kind of like that. Maybe it'll work out. I don't know. Let's distribute. We get 4 e to the t to the 1/2 plus 1. Isn't that 3/2 t minus 4e to the t over 2? And then that'll be a dt. So this is integrable by properties of integrals. We can say 4 here, e to the 3/2 t dt minus, I guess, is there another 4? let's double check. We got to be careful. Yeah, I guess there is. All right, so it's going to be minus 4 e to the t over 2 dt. So each of these integrals now, I'm going to say you guys want to use u sub here, u sub over here, and of course, u is 3/2 t, and here u is 1/2 t. So du is 3/2 dt, or we can say dt is 2/3 du, it looks like. And here we can say du is 1/2 dt, or we can say dt will be 2 du. So we can replace that with this u. It's a different u. These are different u's, different dt's, 2/3 du. Okay, and over here you guys have dt. That's 2 du. So you have a nice sort of situation. I can still do 4, and we're going to integrate now 2/3 e to the u du minus 4 times, well, we'll put that integral, 2 e to the u du. And these are different, you guys know these are different u's. So this is 8/3 integral e to the u du minus 8 integral e to the u du, different u's again. And you go about it, you know, if you want, you could change your limits. Remember, this is t is 0 and 1. T is 0 and 1. So we get 0 for this lower limit and 3/2. And I get here for the other one, 0 and 1/2, because I have to change those limits. Right? Different t values here. Right? T is 0 and 1 for this u. T is 0 and 1 for this u over here. So that changes your limits. Anyway, what I want to say is you guys want to finish this off and get your final answer to integrate, but this is how you start to integrate, where the orientation is, like a nice increasing orientation for x. If the orientation is the other direction, decreasing, then put a minus sign. Anyway, okay. So ladies and gentlemen, we had some good problems the last few days with calculus of parametric equations. Remember, what am I going to do? I'm going to put some examples online for you guys of some of these calculus questions as well. Derivatives, integrals, arc length, and surface area. So I'll give you additional examples. Okay? So again, if you guys have any questions or issues, since we're out of time, come see me during office hours. Those of you that maybe walked in and moseyed in a bit late, check the beginning of the video. We got some good, important information for you guys. And yes, on your next test, which is Monday, May 4th, check the syllabus. You guys get to use a formula sheet for your integrals and your trig identities. And then that's that, right? So be prepared. Think about what's coming. I'm going to add some more homework on this. This was in our book. This was 11.2. This is additional homework. 11.2 additional, I should say. We're going to try to do like 37 to maybe 49 odd, and then 57 to 61 odd. And we're also adding 65 and 66. So here's your additional homework. From that section, this is the integration, arc length, and surface area. And I'll see you guys tomorrow. Okay, take care.